Okay, when we're looking at equilibrium, we can look at it in terms of the aqueous concentration of a species, of a gaseous concentration, or of gas pressures. If we're looking at gases, then we can use the ideal gas equation, and we can rewrite it so that we have pressure in terms of molarity, R and T. And a useful reason to do that is then we can take the equilibrium expression from concentration and write it as equilibrium expression in terms of pressure. So here's a graph of concentration. We start out with hydrogen here. Initial concentration is here. It decreases. Nitrogen is also a reactant. We start with less nitrogen, and its initial concentration decreases until we reach an equilibrium concentration. Ammonia doesn't exist. It's a product, so it has a 0 initial concentration, and its concentration will increase as the reaction goes on. So that's a graph showing what's going on for each of our concentrations. If we look at the balanced equation here, we see that hydrogen should start at a larger amount, and so this amount is, at 3, this is be equivalent to 1, because our nitrogen coefficient is 1. If we put our values into an equilibrium expression, concentration of the product over concentrations of the reactants raised to their particular powers, we get an equilibrium expression in terms of concentrations. If we wanted to write an equilibrium expression in terms of pressures, it would look pretty much the same thing, except instead of concentration, we would use the pressure. So the pressure of ammonia squared divided by the product of the pressure of nitrogen times the pressure of the hydrogen cubed is going to be our equilibrium expression in terms of pressure for this particular reaction. Now, we can get from one equilibrium expression to the other if we rewrite it a bit and we take the ideal gas equation into consideration. So let's start with the pressure. We're going to remember that pressure times volume equals N times R times T. Pressure equals moles times RT. So if I want to take my Kp, pressure equilibrium constant, and make it a K concentration, then I'm going to write this gas law equation in terms of molarity. So pressure over R times T equals molarity. So my equilibrium constant in terms of concentration is going to be pressure of ammonia over RT, and this gets squared, over pressure of nitrogen over RT times the pressure of hydrogen over RT. This gets cubed. Well, the pressures in that configuration is just Kp. So I can rewrite this and concentrate it down and to say that Kp times 1 over RT squared over 1 over RT times 1 over RT cubed. All right, now I can deal with the RTs. And 1 over RT squared over 1 over RT in the fourth in the denominator, so that reduces to RT squared. So what I have then is KEQ equals Kp times RT quantity squared. If I write it in terms of Kp, then I just rewrite it. And since I'm going to divide both sides by RT squared, I can write RT to the negative 2. It's the same as dividing by RT quantity squared. So far we've looked at equilibrium where everything is in the same phase. A lot of our reactions, however, take place with reactants that are in different phases, gases and liquids, aqueous solutions and solids. So we're going to look at what happens when we're dealing with heterogeneous equilibria as well. What this means is when we're writing the chemical reactions, we need to be aware of and make sure we note what is the physical phase of each of our reactants and each of our products. So we're going to take a look at a reaction where we're dissolving sugar in water to make a saturated solution. When we have a saturated solution, there should be solid on the bottom, and as much sugar as possible should be dissolved in the water, and then we have an equilibrium. So when this is the case, then my dissolving rate of the sugar solid is going to equal the rate at which the solution sugar molecules are recrystallizing. So I can write an equilibrium expression for this. Here's my reaction, or actually my phase change process. Sugar plus water, sugar solid. Notice the physical state here. Water's going to be a liquid, so we'll put an L here because that is important. And then here, sugar is an aqueous solution. So there's my physical state for all three things. Here's my equilibrium expression. The solution is in the numerator because it's a product. In the denominator, I have the concentration of solid sugar and the concentration of water. Remember the definition of concentration. It's the number of moles of solute per volume of solution. Concentration of the sugar solution is the only thing where we have a molarity. So our equilibrium expression is just that. Why is that? Well, sugar solid has a specific density, and that is the mass that we have divided by the volume it occupies. As the mass increases, so does the volume. As the mass increases, so does the moles. So this ratio stays the same, and the concentration doesn't change. I really can't have a concentration because the moles and volume don't change. Water is the same deal. As I increase the amount of water, I increase both its mass and its volume. And so I'm not changing its concentration. It's a pure substance, so it really can't have a concentration. So both my denominator values have values of 1, and so that's what gives me this equilibrium. So that's what gives me this equilibrium expression, just in terms of the products. Another example, I look at calcium carbonate decomposing. Calcium carbonate's a solid, so I'm heating it, and I get calcium oxide, which is also a solid, and carbon dioxide, which is a gas. So I have a heterogeneous reaction going on here. Initial equilibrium expression, taking everything into account. I have calcium oxide and carbon dioxide as numerators, because they're the products. Calcium carbonate as a denominator, because it's the reactant. But calcium oxide, calcium carbonate are solids, so their concentrations are effectively 1. So the equilibrium expression for this is just in terms of the gases. What this means then is solids and pure liquids are never part of an equilibrium expression, and that's really important to remember. However much solid I have in a reaction, if it's a reactant or a product, it's never going to be part of the equilibrium expression, so it's never going to change the equilibrium. Take a look at what information the equilibrium constant gives us. So when we determine the equilibrium constant, it indicates the direction of the reaction. When I have a K that's bigger than 1, that means my numerator is bigger than my denominator. I have mostly products. When K is less than 1, my numerator is smaller than my denominator, and that means I have mostly reactants. The K for equilibrium is not at all related to the K for kinetics, rate constant. They're totally unrelated. Unfortunately, they're the same letter, but they're not related. You can have a really large equilibrium constant, which means that you're going to get mostly products, but it can go at a very small rate. For example, iron plus oxygen going to iron oxide has a very large K, but the rate constant is very small. It takes a long time for rust to form, relatively speaking. You can have a very small equilibrium constant, but the reaction happens very quickly. So that means that the very little bit of reactants that do react will happen quickly to form products, but you don't get very much product formed for the particular reaction. And the equilibrium constant depends on change of energy of the overall reaction, but the rate depends on the activation energy. So they both depend on energy in a sense, but they depend on different amounts of energy and different types of energy. So they are related, and when we get to our chapter on thermodynamics, chapter 16, we'll tie them all together and see how they are related to each other as well.